Okay, ladies and gentlemen, welcome to our talk on bootstrapping linear programs in value iteration algorithms. As you can see, the talk is not only about MDPs, but also about related problems. That is because our method is general and across, and can be applied across different problems that have linear programs inside of their value iteration schemes. Some of these problems are multi-objective Markov decision problems. I'll talk a bit more about them in a minute. Partially observable Markov decision process, which I don't have to tell you anything about probably. Zero-sum Markov games. And these can all be solved by iteratively solving increasingly similar linear programs. And this is because after there is a bootstrapping, so we use a Bellman update. And in this Bellman update, we update sets of value vectors. And then we use a pruning operator to prune these sets. And our main idea is that we can bootstrap the LPs from previous iterations in order to make this pruning a lot faster. All right, so in this talk I'm going to focus on multi-objective MDPs and partially observable MDPs. So first of all, the partially observable MDP I probably don't have to say a lot about, just that we have a value function, and this value function is typically described as a set of alpha vectors. And so these alpha vectors, together with the belief of in which state you are, gives you a scalar value. And so the value function is actually, without the belief, it's just a set of these alpha vectors. And it's piecewise linear and convex, as you all well know. So you're probably slightly less familiar with multi-objective MDPs. However, this is a problem that has been gaining traction quite a bit over the past couple of years. It actually poses a very important problem already by Bryce in 2007, who argued that any type of probabilistic planning is in fact already multi-objective, as there's always some cost associated with the plan and there is a goal. Furthermore, this year an article came actually out in the philosophy journal that said that human-allied artificial intelligence is a multi-objective problem in itself. And so that means that whenever you have some type of user and you need to align your AI in order to user preferences, then it's already multi-objective. And then finally, and this one I found particularly interesting, is that Tim O'Reilly said that the economy is running on the wrong algorithm. And it actually says, oh, we're just optimizing for money, and really we shouldn't. We should be optimizing for different things in parallel. And that, of course, again, leads to multi-objective problems. So I hope I have convinced you that this is a very important problem. So what do they look like? Well, they look like the regular MDPs, just with a vector-valued reward function instead of a scalar one. So now we have n objectives. And this naturally also leads to vector-valued policy values. And so there is no longer a single optimal policy. Okay, then what do we do? Well, first of all, we follow the utility-based approach, which we proposed in 2013, which says, well, we can assume that there exists some utility function that maps this vector-valued policy values onto a scalar value, a utility. It's just that we don't know it. And we don't know it during planning or learning, and then we have to interact with the user later. So one of the very common assumptions about this is that we can assume that it's linear. And this leads to a inner product between a certain weight factor, which can be assumed to be on the simplex. And this, for example, corresponds to the utility score corresponding to the different elements of the vector corresponding to units that we can sell in an open market. And then these weight factors become prices that can vary over time. If this is the case, then we need to compute what we call a convex covert set, and that looks like this. So if we have multiple policy values as points on the left there, then for example in a two-objective problem, if we transpose that and we define the scalarized value function as just the inner product and the value function of different policies, then again we get this nice piecewise linear and convex value function on the right. And so this means that we can use the same type of linear programs that we use for MDPs. All right, so the state of the art in multi-objective MDP planning is still convex hull value iteration, proposed by Barrett and Narayanan in 2008. And it looks very simple, and it looks very much like VI, so it uses these same Bellman backups, except that now we have these sets of value vectors. And after every backup, we have an intermediate convex covert set. So here are just the formulas that correspond to it. So we need some kind of initial set of value vectors to start with. So for example, the singleton set with just a 0 vector in it. And then the Bellman backups look, well, pretty much like we're used to. We have the transition function, and then we marginalize over the possible next stage. And then we have the immediate reward and the value of the next state. However, now if we want to marginalize over the next state, we don't actually have a simple sum, but we have a cross sum where we can combine all kinds of different vectors from the sets that we input. And then after we've done this, then we actually have to prune this set back to exclude vectors that we do not need. And so this pruning after every next state corresponds to what we know in MDPs as incremental pruning. All right, and then finally, after we've got all Q values, then we take the union over all actions, and then we prune again. And so this cprune uses, again, linear programs. Okay, so now I've gotten through all the background, so now let's go to our main contribution. How then do we exploit these different LPs that we've already computed in previous iterations? So we start with the observation that this pruning happens every iteration again. So every full Bellman backup, we compute a bunch of these pruning operators. We do this after every transition, while computing every QSA value, and then when computing every VS function. And so this provides us a certain context, so this SA S prime, and just S, and these are contexts, and within these same contexts, the linear programs become increasingly similar. And we can exploit this by bootstrapping the LPs we use for this pruning. So, where then do we exactly prune? Well, first of all, before we prune, we compute a big set of all kinds of vectors, and we're trying to remove vectors that we don't need. And so we expect these vectors one by one from the input set, and then we add them to the intermediate solution set iteratively by identifying a point or a weight where it maximally improves the intermediate solution set. And in order to do this, we need an LP. So if there's then no improvement, we just throw V away, and else we find a vector from S that is best at this weight, and we add that vector to the intermediate set. Okay, now let's look into the LP. So in order to compute this maximal improvement, we look at the vectors already in the intermediate coverage set, and then we add multiple constraints according to that formula over there. So then we find the point where the maximum improvement is, and that looks somewhat like the picture on the right. So we are looking for these different points. The lines are constraints that we already have, and then the optimal and maximal improvement is given by the black point over there. All right. Good. So then we apply one more trick that is vital to know about. And that is, we iteratively generate the constraints, and then we solve way smaller LPs than if we were to add all the constraints at once. So we solve the LP for a given set of constraints, and then we iteratively start adding constraints by given a belief for a certain constraint, finds the constraint that reduces the objective value the most. So this is called Bender's decomposition, and this is a nice iterative scheme again. And the point about this is that if we have very many constraints, then the constraints that actually are relevant for the optimal solution is actually equal to the number of objectives we have in a multi-objective MDP, or the number of states that we have in a POMDP. And so we typically don't need all the constraints to find the optimal solution to the LP, and therefore this decomposed version, even though it serves a series of LPs, is typically a lot faster still. All right. So, if we do this iterative constraint adding procedure, then we can actually use the constraints that are most similar to the ones we've seen for the same context inside our value iteration algorithm from the previous iteration. So in the ith iteration, we already had a set, so we already had a solution to our LPs, and now we try to find the closest possible new constraints that corresponds to the constraints where we found the optimal solution in the previous iteration. And that gives us a initial set of constraints for which we don't actually have to iteratively add all the constraints from the extrema as we did previously. And so again, this is can be a big step. However, in order for this to work well, the input sets that we provide to the pruning operators needs to be ordered. And this is just because the same constraints, the constraints need to be the same for every vector that we add. So the most similar to the previous iteration for every vector that we add. This takes a bit of time, of course, so it adds some extra administration. Okay. So we do add a bit of extra administration here, and the sorting takes time, so we expect that the performance will be better and better as long as the Bellman equation, so the residual Bellman error goes down, so as the number of iterations improves. Yes. So now let's see whether that's indeed the case. So first of all, let us have a look at the number of LPs, so the number of times that we run this slave LPs as a function of the Bellman error. And you can see that for example, for a 45-state multi-objective MDP, we see that as the Bellman error decreases, note the log scale, that we can compute less and less LPs than if we were just used to do the iterative constraint generation as previously defined. So we're computing less than half of the LPs. The same is true for exact value iteration in POMDPs. All right. So of course this leads to some nice reductions in runtime. And first let's start with the POMDP results. So these are a bunch of different POMDPs from the literature. And you can see on the left there is iterative content generation, which was proposed on AAAI last year, right? And so this is this iterative constraint generation scheme, and then our bootstrapping LP actually reduces the runtime significantly. So it's a reasonable improvement. However, the major improvement actually appears when we look at multi-objective MDPs. So here, for example, is the runtime that we can achieve for multi-objective MDPs as a function of the number of states. And there you see that even though, so that as the runtime increases, we compare to 2. So our algorithm is the black line, and then we have the iterative constraint generation, and just the vanilla LPs that don't use any iterative constraint generation in the gray and the dotted lines. And so this is actually a very significant improvement, and then also note that because convex hull value iteration is the state of the art, this is actually just cutting a third of the runtime up to 50 states, and actually the difference improves over time. All right. So if we look at this in table form, for example, for a bunch of different states and values for states and objectives, then we see that the number of LPs that we compute goes down significantly, and the bigger the MLMDP gets, the better the improvement. So this actually scales better both in the number of states and the number of objectives. And this is, of course, very relevant for multi-objective MDP solvers. All right. So in conclusion, in VAs, in value iteration algorithms based on LPs, these LPs become increasingly similar over time, especially as the Bellman residual error decreases. And the constraints within the LPs can be bootstrapped in order to jumpstart the LP solver. And this leads to significantly faster pruning, which leads to a significant improvement in the state of the art for exact value iteration schemes with LPs. Okay, thank you for your attention.
Thank you. Any questions? Oh, just a second. Just a second. Ask not to throw too much.
Hi.
Hi.
So first I was surprised to see no comparison to Lark's algorithm for pruning alpha vectors. I assume that you do much better, but still it would be nice to show it. Are you aware of the skyline algorithm for pruning?
Yes.
So I think that what you're doing is very similar to the iterative skyline, where you start from a point in the upper envelope and continue from there. That's very similar to your bootstrapping, isn't it?
Erwin, could you help me out here?
Within the skyline algorithm, you have a kind of procedure that is very similar to the simplex iterations that you would run in case you implement plain simplex, right? Mm-hmm. In that sense, it's kind of similar. I think it's not exactly the same, but we can talk about it. I've looked into that.
Yeah, would be interesting.
Other questions? I wonder, so these are exact algorithms, and they don't scale too well. Okay. Have you thought about any options of using these ideas in approximate algorithms and some, I don't know, in some MDP algorithms now, people use LPs to generate heuristics or things like that?
Okay. Yeah, so my answer to that is twofold. So first of all, let me point out that for multi-objective MDPs, CHVI is actually the state of the art. So that's actually, exact algorithms are very much applied there. And so there is not a lot out there for approximate algorithms there. And so our method actually generalizes across different types of market decision problems that have LPs in their value iteration schemes. However, yes, we have looked into some papers that do approximate value iteration schemes with for MDPs. However, we haven't implemented it yet, but we are definitely planning to work on that.
Okay, thank you. Any more questions? Okay, let's thank the speaker.